Right. So hi everyone and welcome again to Math 027. So for this video, I will discuss the probability distributions. To be exact, I will only discuss the discrete probability distribution and in general the random variables or how do we uh, represent a random variable. So for the outline, I will only discuss the discrete probability distributions, so binomial and Poisson, and then the random variables. So for the next video, na lang yung continuous probability distributions. So the intended learning outcomes, we want to solve for the probabilities of discrete and continuous distributions in general. Okay. So let's discuss the random variable. So what is a random variable? So random variable is a representation of the possible events or sorry, the random variable is represent representation of the possible numerical value from an uncertain event. Okay, so later I will discuss this through an example. So there are two types of random variables. We have discrete random variable and a continuous random variable. So what is the difference between the two? So discrete random variables are countable. And usually we're talking about positive integers when we say discrete, no? But it is well in general it should be integers. But since this is a statistics class, usually we utilize only the positive integers including zero. And then for continuous random variables, so it is continuous, therefore including the decimal places of your numbers. So we're usually dealing with uh, numerical values that are not limited to countable numbers. Okay. So we have examples of discrete random variables and continuous random variables. So the first example for discrete is the number of sales, number of calls, shares of a stock, people in line, mistakes per page. So as you can see, these are all countables, no, by hand, usually. And then continuous random variables are length, depth, volume, time, and weight. So you can see that length has a numerical value or it could contain decimal places. That is the only difference, no, of continuous variables or continuous random variables from the discrete random variable. Okay, now so let's talk about the discrete random variables first. So let's say you have a dice, no, and or a die for singular, no? And you let's say you want to roll the die twice. Okay, so you have four possible outcomes for rolling a single die, but if you want to do it twice, then we can represent some random variable depending on what we want to represent. Let's say we want to represent our random variable as x, which is the number of times wherefore will occur. Okay, so at rolling that two dice, you can imagine there could be numerous cases. So the first case should be you will not roll any, no? So any of the two dice, you did not roll any of the two dice, the number four. Or you can roll only one four die, no? Or you can roll both two fours. Okay? So that is the random variable, no? A representation of the event that is uncertain. Now, let's talk about probability distribution. So the probability distribution of a discrete random variable is usually provided as a histogram, using a graph. And it specifies the probability of each outcome of the random variable. So I'll just show you later, what does it look like, but it is generally just a histogram, you know. So there are two important properties of random variable. So the first one is that it will always be positive, ano? Or zero. And then the sum of all the probabilities of the random variable will be equal to 1. So the summation of p is equal to 1. Okay, so let's consider again the previous problem. So we tossed two coins or anyways, let's consider a new problem pala, ano, sorry. So let's consider a new problem and we want to, let's say, toss two coins. So let x be the number of heads or our random variable. So as you can see here, there are four different outcomes. So it could be two tails, a tail and a head, or a head and then a tail, or both heads. So how do we represent this discrete random this discrete random variable? So for the discrete random variable x, so how many number of heads is the first case? No, we have two tails, so this will be just zero. No, so there is a case where there is zero number of heads. There are two cases where we have two number of heads, and then there is only one case wherein we have two number of heads. So now we can figure out the probability of this random variable. So if you want to figure out the probability that there will be no head, then this will be 1 over 4, which is 0.25. If you want to see the probability that it will have exactly one head, that will be 0.50. And if you want to have it, if you have to have two heads, then this will be 0.25 or 1/4. So what is the probability distribution? That, yes, this is already the probability distribution, but the graphical representation is this. So as you can see, it follows this. We have some pattern here that is that looks like some form of a normal distribution, ano? But it doesn't really mean that it has to be a normal distribution. So what does the probability distribution tell us? Ano? The probability distribution tells us that what are the or how does the random variable behave, no, with respect to its probability. Okay, so the sum of these three random variables, no, cases, should be equal to 1. So 0.25 plus 0.5 plus 0.25 is 1. Now, we can consider a more complicated scenario. Let's say we want to consider tossing three coins, and then still x will be the number of heads, which is also our random variable. So there are 8 cases here. So we have 3 heads, 2 heads and a tail, and so on. So we can count here the probabilities of each of this happening will be 1 over 8. So the total sum will be 1, no? And then for the random variable, how many heads does each of the case have? So for the first case, we have 3 heads, okay? And then for the second case, we have 2 heads, and so on. So we can count here the probability of the random variable from happening. So for exactly 3, now we have only one case. So that will be 1 over 8. For exactly 2, no? So this one. For exactly 2, since we have 3 cases here, then this will be 3 over 8, and so on. So for one heads, at least, exactly one head, then this will be 3 over 8, and then for no heads, this will be 1 over 8. So that is your probability distribution in this form or in tabular format. Okay, for its graphical representation, we have the histogram that looks like this. Okay. So with the probability distribution graph, we have an idea, no, how the random variable behaves with respect or the probability behaves with respect to its random variable. So that is a random variable. Now we have special characteristics of random variables. We have the mean. You can find the mean of your random variable. So how do we figure out the mean? We can just find here the summation of the multiplication of the probability of that random variable from happening multiplied by its random variable value. So the expected value is again just a summation of this. Okay. So for example, we have this tabulation. So therefore, the expected value will be 0 times 1/4 plus 1 times 1/2 plus 2 times 1/4. So the total of that will be equal to 1. So the mean or the expected value that is synonymous is equal to 1 for this case, no? For tossing two heads, sorry, two coins, no? And the random variable is the heads. So we also have another characteristic or two other characteristic of our random variable. We can also figure out the variance and the standard deviation. So for the variance, that will be the summation, the square of each of the random variable numerical value minus the expected value or the mean of the random variable multiplied by the probability. Okay? So therefore, the standard deviation is just the square root of your variance. So just find the square root of that. Okay? So let's say, for example, we have this case again. So tossing two coins and x as our random variable, we want to compute for its standard deviation. So how do we do that? We already calculated its expected value or the mean, which is equal to 1. So therefore, we just use this formula. So we already know as well the x variable for each of the rows and its probability. So therefore, the calculation of this will look like this. So we started with 0, 1, and then 2, and then hanggang 2 lang pala, no? And then the expected value is just 1. So 1 for this, 1 for this, 1 for this. And then square that, and then find the probability or the respective probability of each random variable. And then find the square root to find the standard deviation. So the answer should be 0.707. Okay, so that's it. Okay. So we can apply this in investment, no? And we have this example wherein, let's say we want to invest 10,000 pesos, and we want to decide on two options, no? We have the passive fund and the aggressive fund. So basically, if you apply on the passive fund, there are three cases, no, that might happen with your fund. So recession, meaning your investment might decline. Stable economy means that there is no change, or there's not much change in the economy. And then expanding economy, we have a faster change or high economic growth in this scenario. So for the passive fund, there are three cases. For the aggressive fund, there will be three cases as well. So for the aggressive fund, the risk is quite high, no? So you might lose 2,000 pesos if in case there will be a recession or pagkalugi or a downward economic growth. So, but to relate to that, there is a high return if it grows, no? If the economy expands. So choosing for either this or this one, we can utilize the random variable principle. So we can compute for its expected value for, let's say, x and y. So we have two random variables here. We have to compare these two random variables. So to find the computed the computed expected uh, value of the first random variable, which is your passive fund, which is x. So that will be just the multiplication of its probability and its random variables. So we have negative 250 times 0.2 and so on. So we have this multiplication. Okay, and then sum that, we have 500, and then do that as well for the second fund, which is the aggressive fund y. So as you can see, we have a higher expected value for the second scenario, no? So we might opt to choose the second option since on average it will give us a better return. Okay, so it will give you 950 pesos return compared to 500, which is the passive fund. So it seems to be much more practical to invest in the aggressive fund since it will gain we will have a better gains. Now if we now compare their standard deviation, okay, So standard deviation could be a measure of how volatile or how erratic our decision can be. So how erratic or how crazy it is changing, no? So for the first case, for the passive fund, we have only 433. But for the aggressive fund, we have a higher value. Therefore, what can we say about this? Even though the aggressive fund or fund Y has a higher average return, it is subject to more variability compared to the passive fund. So the probability of loss might still be higher. Ano? So the higher, you will have a higher gain and average, but you might lose a lot if you invest on the aggressive fund as well. Okay? So what we just did is we computed the expected value of two random variables, but we can also find the expected value of the sum of the two variables. So there are properties here that we should be familiar with. And so for the expected value, you just add this two. For the variance of two variables or random variables, we can find the square of each, and then we can also add twice the variance of the multiplication of x and y. Okay, so that's it. And moving on from random variables, we will now describe the probability distributions. So what are probability distributions? Again, it is just a representation of how the probability is distributed across the random variable. So there are two types of probability distribution. So we have the discrete and we have the continuous probability distribution. Now, we will only discuss the two, discrete probability distribution, and we have the binomial distribution and the Poisson distribution. So first, for the binomial distribution, let's say we have a fixed number of observations n, and let's say that case is just tossing a coin 50 times, okay? Or another scenario might be uh, 10 light bulbs taken from a warehouse. So, what? I think this is not included, no? Huh? 10 light bulbs taken from a warehouse. Why? I think this is not included, sorry. So we only have 15 tosses of coin. Now, what is a binomial probability distribution? So usually if we have a case wherein we have two possible outcomes, it will happen or it will not happen, or basically if it will succeed or it will not succeed or it will fail. So if we have two choices or two possible outcomes or two possible general outcomes, then we can utilize the binomial probability distribution to predict how will be the or what will be the probability for such event that it will occur at n observations. So from the name itself, binomial, so we have two possible cases. Okay. So another example here is we have head or tail for tossing a coin. It could be a defective or not a defective light bulb. And since the okay, so most of our assumptions here in the binomial probability distribution is that the two categories, the success and the failure, should be mutually exclusive. So there should not be an intersection, and it is collectively exhaustive, meaning either it will happen or it will not happen. Okay, so constant probability of the event of interest for each observation. So let's say we want to figure out the success rate of tossing a coin 5 times. How many tails is that? So we can figure that out, and we could let P as the success rate of having a tails. So that will be 50% since toss coin will be 50-50 if it is a fair coin. Okay, so the observations are independent. So the outcome of the first experiment or first trial will not affect the second trial and the third trial and so on. And two sampling methods deliver independence. So we have two cases here, infinite population without replacement and finite population with replacement. Now, on what scenario should we use the binomial distribution? So there are possible applications here. So we want to know whether we properly labeled items as either defective or acceptable, or how we want to get the chance if we will get a contract or not, or how do we distinguish if our product or our customer will want to buy the product, no? And then as employers, we want to know the probability that the job applicant will accept the offer or not. So usually if you have yes or no, success or fail, then you will have binomial distribution. So we have here an example of binomial distribution. So suppose an event of interest is obtaining heads on the toss of a fair coin. You are to toss the coin 3 times. In how many ways can you get 2 heads? So there are how many ways? So we have 2 cases where we have 2 heads. Sorry, 3 cases pala when we get exactly 2 heads. So we can just count, no? The number of ways and then over all the cases. But there is a simple way to do this, or there is a distinguished formula that we can figure out what is the probability of this happening. And that will be using the binomial distribution formula. So the binomial distribution, or this is actually the probability distribution function. What is that? Why is this a function? Because it is represented that we can find the probability as a function of the x, the n, and the probabilities. So there are different variables or independent variables that affect our probability. So again, n is the number of trials, x is the number of successes that we want to figure out, and d is the probability of success. Okay? So let's have this case. So the probability that a certain kind of component will survive a shock test is 0.05. Find the probability that exactly 2 of the 4 components tested survive. So we have so you only have 5% chance in succeeding this shock test, and we want to know the probability that exactly 2 of the 4 components will survive. So how do we determine this? Now, we can just use the formula. And what are the variables or what are the givens here? So n is 4. Since we have 4 components, total or 4 number of trials, and then the probability of success will be 5% or 0.05. Therefore, we can just substitute this to our probability distribution function or the formula in general of the binomial distribution. So we just substitute p here. We have n, and then how about x? So the x here is, actually this is the probability distribution function. So the independent variable left here is the x, or the random variable x. So if we substitute the variable 2, since we want to figure out the probability of exactly 2, then we can just substitute x here as 2. Then the probability of that happening will be 0.0135. So about 1.4% that this will happen. No? 2 out of the 4 components tested will survive. Now, another scenario here. So the probability that a patient recovers from a rare blood disease is 40%. If 15 people are known to have contracted this disease, what is the probability that from 6 to 8 will survive? So how do we do this now? Okay, so remembering what is the probability, binomial distribution, binomial probability distribution. So we have 2 cases here. There is 40% chance that the patient with this disease will recover, and 60% that it will not recover. So therefore, it just says that there is a 60% chance of fatality, no, or fatality. So therefore, we want to find out what probability is when 6 to 8 will survive. So we should consider when 6 survive, 7 survive, and 8 survive. So that's it, no? And then defining this as your probability of success, and n is your 15, then therefore, we have the calculation here. So the probability distribution function will be this. So substituting the n and the p, okay? And then substituting the x here for each of the cases. So basically, we have to just substitute here 6, ano, for the first case, and then another case is 7, and then another case will be 8. So add these 3 distributions, then we have what do you call this? The total probability that from 6 to 8 will survive. So we have this, substitute 6, and then 15 minus 9 is, 15 minus 6 is 9. So we have 7, 15 minus 7 is 8, and so on. So therefore, the probability that 6 to 8 will survive will be about 50.17%. Okay? So let's change this again. So how about when at least 5 will survive? So how do we do that now? So what can we do is instead of calculating, no, what we can calculate is we have 2, 3, 4, and up to 15. So in avoiding that scenario that we have to calculate everything from 2 to 15, since we say at least, ano, we can just find, what we can do is just find the probability that that no one will survive, so 0, and 1 will survive, and 2 will survive. Okay? So we can just add this 3 cases, and then subtract this 1 from this probability. So the probability that this will happen, or 2, 0, 1, or 2 will survive. Sorry, actually not including 2, so 0 and 1 only. And then subtract 1 from that so that we can get the complement, which is also the at least 1 will survive. So what we can do here is again substitute the value of the success and the probability. And then what we can do is we can subtract the probability that this 2 will only 1 will survive, or no one will survive, which is basically just this will be equal to 1 minus the probability of x is equal to 0, and actually plus, so bracket and then p, x is equal to 1. Okay, so basically this will be just we have 15c 0, and then 0.40 raised to x, so 0, and then 0.60, and then we have 15, and this one will be 15c1, 0.40 raised to 1, and then multiplied by 0.60 raised to 14. Ayan. So if you add this 2, then you will have 0.005172. Therefore, the probability that at least 1 will survive will be a high number, no, expectedly, which is 99.14%. Okay? So it is that simple, no? So now we already solved some examples here. Now let's discuss the binomial distribution shape. So we have two cases here that I want to discuss. So the binomial distribution shape, or the probability distribution function, no? Basically, the shape of your probability distribution function, or PDF, is equal to this. So let's say we have n and p is equal to this. So we have the shape. So the shape is dependent upon the number of trials and the probability of success. So for that case, we have this shape. For n is equal to 5 and p is equal to 0.5, we have this shape. Okay, so what can we realize here? No? So if the probability is closer to 1/2, then usually it will look like a mountain, no? But if it is lower than 1/2, usually 0.1, then this will look like a slide, no? Or the other way around, if this is 0.9, so it will look like this. Okay, it depends on the case. So that is basically the probability distribution shape. So the cumulative probability is uh, uh, what we just did last time, no? So we can add the probabilities of each of the random variables to get the total or the cumulative probability. Now, so let's say for example, we have n is equal to 4 and p is equal to 0.75. So if we substitute this to our formula or the probability distribution function, then we can see here a cumulative value. So if x is equal to 0, we have 0.0039. For x is equal to 1 plus x is equal to 0, then this will be 0.2617. And cumulatively, no, so this should add, every probability should add into 1. You should remember that. For the cumulative probability distribution, there are, this is the graph, no? Or how does it look like? It will look like this. So again, no, if it is closer to 1, usually we have this slide that is looking like this, no? So we can determine from this graph the approximate probability of, let's say, when the random variable x is less than or equal to 2. So basically, we just add these three probabilities to get the probability of success that at most 2 will be successful. Okay, so what are the characteristics of a binomial distribution? So we have the mean, variance, and the standard deviation. So for the mean, you can just multiply the probability and the number of trials to get the expected value, okay, or the mean, mu. For the variance and standard deviation, we can find the variance as n times p, so the number of trials and the probability of success multiplied by 1 minus p. For the standard deviation, just find the square root of the variance. Yeah. Okay. So for the binomial distribution characteristics, so we have an example here. We can find the mean and the variance, the standard deviation of this binomial distribution function. That is when n is equal to 4, n is equal to 5, and p is equal to 0.1. And then for n is equal to 5 and p is equal to 0.5, so we will have this, no? So we have the mean 2.5, and we have this standard deviation of 1.8. So what can we say about this, no? So if we have a mean of 0.5, meaning the mean here is, what is the mean here? So the mean here is basically just in between here, no? So most of the probability is within this portion, no? Or somewhere between 0 and 1. For its standard deviation, it is not that varying, no? So it is mostly focused in between 0 and 1, so that is why it has a low standard deviation. For the second case, as you can see, the mean or the expected value is 2.5, so meaning the majority of the data or the mean value of the data is in between 2 and 3. So this is 2.5, for example, now. And we have a higher standard deviation here because the data is quite dispersed, no? So it is not focused on a single or in between the mean. Okay, so that's it. For the Poisson distribution, so the last portion of our probability distribution function. So the Poisson distribution is when you are interested in finding the probability that an event will occur given an interval. So usually an interval is a continuous time, but this is also applicable for discrete times, no? So the shape of the probability distribution function of the Poisson distribution will depend upon the parameter lambda and the random variable x. So actually, the Poisson distribution is just an expansion of the concept of the binomial distribution, wherein the Poisson distribution has a number of trials that is infinite, or a limit that is approaching to infinity. I will not show the derivation anymore, but you can look up the derivation online or in our textbook. But we have this formula as our distribution function. So what does this mean? No? So we have the probability of this happening using the Poisson distribution. This is equal to E. So Euler's number raised to negative lambda. So the lambda is number of events occurring at that certain interval. And then we have x here. So lambda raised to x. So x is just the random variable or the number of events in that interval. And then we have over x factorial. So for example, we have a lambda of 0.5, then we will see a distribution that looks like this. If we have lambda that is 3, it will look like this. No? So as you can see, the lambda actually also represents the mean. So you can see the middle of this distribution function. No? So you can see we have 0.5, about 0.5, 0 and 1 is about the average of this histogram. For the second graph, we can see that the average of this graph is about 3, right? So usually I will discuss this later, but the mean of your Poisson distribution will also be your lambda, or the expected number of events. So the scenarios that we can use the Poisson distribution is when usually it is the time is continuing to happen. No? So you want to find the probability that how many number of scratches in your car paints will be at this given interval, no? The number of mosquito bites of on a person during this interval, no? What is the probability of that happening, and so on. So there are countless of ways that we can use the Poisson distribution. So for this example, it is known that cars arrive at the drive-thru at a rate of 3 cars per minute between 12 noon and 1 p.m. If the number of cars that arrive in any time interval is a Poisson distribution, what is the probability that exactly 10 cars arrive between 12:10 and 12:15? So what can you say about this? So it is already said in the problem that it will have a probability distribution of a Poisson type. We want to find the probability that exactly 10 cars arrive between 12:10 and 12:15. So what are given here? So we have a rate of 3 cars per minute between 12 to 1 p.m. So what can we say about this? So during that interval, no, so we have to know the probability of 10 cars arriving at that interval from 12:10 to 12:15. Then how many cars, no, on average, no, it seems, at that interval will arrive, no? So we have 3 cars per minute. Therefore, we can do here, actually, no. 3 cars per minute. Okay, so we only have 5 minutes, right? So 5 minutes only. So during this 5 minutes, how many cars will have arrived? So the Poisson distribution here, the lambda will be equal to 15. So because we only have 5 minutes, and at that 5 minutes, 3 cars per minute will arrive. So therefore, the number of cars average basically using the Poisson distribution will be 15. So 3 times 5. So now, what is the random variable? So the random variable here is 10 exactly. So therefore, we want to find the probability that x is equal to x. Wherein our lambda is 15. So we can substitute the formula here, or the values to the formula. And then we will substitute the value of the x here, which is 10. So substituting 10, we have a probability of about 5%, or 4.86%, that exactly 10 cars will arrive. Okay. So another scenario here, what is the probability that at most 5 cars will arrive between this? So the lambda will still be this, and the probability distribution will still be this. Now, if you want to find what is the probability at most, no, 55 cars. So basically, we're trying to find the probability from 0, no, up to how long, no? So up to the probability that it will be 5. So at most 5. So therefore, we want to find this total probability. Now, how do we find that? What we can do, guys, is we can just use your calculator, no? So a trick here, so the trick here, you can use the sum function here. So we have a sum function in our calculator. So the sum function here, so we have this. So we need to know what is the probability from 0 to 5. So to save time here, what we can do is just input the function here. So we can just input here e raised to negative 15 and then multiplied by 15 raised to x and then all over x factorial. So x, sorry, alpha x and then factorial. So we have factorial here. And then what we will do, so we started with 0. So we input here 0 and then we ended with 5. So this will be 5. So we can solve that using this formula. So we have 0.0028, or we can change the decimal places, no? So this will be 0.00279. Okay, so that is a quick way to solve this problem using your calculator. Okay, so I'll just put this back. So 4 again. So I think that's it for this example. So again, the characteristics of a Poisson distribution. So if you want to find expected value or the mean, it is just the lambda. And then the variance of your this distribution will be also the lambda. It is quite interesting, no? And then the square root of the lambda will be your standard deviation. So that's it. So thank you guys for listening. I hope you understand something here. See you guys on Tuesday next week. Bye.